So what is it about control? What control engineers really do? Do they only design one magical PID on every industry and bring all the multi-variable systems to their desired value? No, we are more than that. I'm Saraf Shariati from the Institute of Automatic Control. I'm a PhD student and research assistant, and today I'm trying to introduce what we do, most of us, model predictive controllers in the field of hybrid vehicle systems. At the very beginning, I just give you some background on the control strategies. Then we just look at how we can use model predictive controllers in the industrial systems. And at the end, we just go back to the hybrid vehicles and see that what do really model predictive controllers can do for us. So this is a very conventional loop of control concept, which probably you are all familiar with. And what you can see that we have one manipulated variable. This is probably the variable that we decide and we give it to the system. At the end, we have some controlled variables. These are variables that we want to control, we want to guide towards one special reference, and we probably need to measure them by some sensors. So the loop is completed by one control unit, which takes the controlled variables from the plant or sensors and give the decision to the actuator. We have mainly two different types of strategies. The first one is the feedback control, which takes the measurements, and the second one is feed-forward control, which is based on a priori information. I'm not focusing mostly on feed-forward control, but mostly on feedback control, how we can handle the measurement, and how we can design our strategy based on the measurements. So at the beginning, I started with a PID controller, which is the most conventional strategy. How do we do that? How do we simulate our systems? Can we just design one controller and put it on the system? Shouldn't we first convince our boss or the person in charge that actually our control strategy is working? Yes, we have to convince them. The first thing is that we have to first have a simulation of our system, test our controller, show that this is actually really working, and then we are allowed probably to put it on the real system. So the first step with designing the controller is to design one simulation part. The simulation part is usually done with MATLAB Simulink, which is the most powerful tool that we control engineers work with. The MATLAB is speaking for itself. This is the Matrix Laboratory, is a very convenient tool to work with matrices and vectors. So first we can try to simulate our control strategy. In the second part, we can use different control toolbox and analysis of the MATLAB to analyze the stability, run different type of analysis, and check the different aspects of our control strategy. And at the end, we can program, because MATLAB has a very good environment for programming. We can program there, and we can compile it to C, C++, Java, whatever your real-time machine demands. Here I want to give you one simple example. This is a very conventional example, seems very primitive, but if you're a chemical engineer, you probably have dealt with it a lot. In the chemical industries, we have a lot of reactors. We have a lot of distillation columns, CSDRs, which is pretty much similar to the same structure that I'm showing you, in which there are different tanks connected to each other, and you want to control several parameters, including the level of the fluids, the pressure, the flow in these tanks. What I do have here first as the manipulated variable is the input flow. Then I have the controlled variable, the one I want to control. This is the level of the water in the third tank. I have different states of the system which I cannot influence very directly, but they are important. And then I have some parameters which I can measure, and they influence my system. These are measurable variables. So the first step in designing a controller is describing my system. What we usually do is using ordinary differential equations. Based on ordinary differential equations, we can make a platform. For example, for this system, I have 3 different tanks and 3 different flow meters, which are made based on ordinary differential equations. For example, for this system, I have 3 dynamic level of the tank, which are described based on different parameters of my system, including output, including main output, including measurable disturbances, and the time. In the next step, I have to describe my measurable or controllable variables based on the different variables I have. Here I have my output, which is the level in the 3rd tank, described based on states of the system, input of the system, measurable variables, and the time. So I put everything in this block, and then I design my PI controller, which gives me 2 degrees of freedom. The first one is the gain, by which I can say how fast must my system be, and T, which is a time constant, which is based on my model. I give a feedback loop. I say what kind of set point I would like to have, and at the end I have my control strategy. Let's take a look at what is happening when I apply my PI controller to the real system. You see that this reference, which is the red line, is at the beginning on roughly about 5 meters. The level in the tank, in the 3rd tank, is gradually coming up, has a little bit of overshoot, and then at the end ends up on the reference. I'm happy with this, so I change my reference to a higher value. The input of the system is going to be bigger, and the level of the tank is gradually coming up, have a small overshoot, and then go back again to the reference. At the end, I would like to empty my tank. So my PI controller decides that the input should be 0, the level of the 3rd tank is coming down. What do you think is the problem here? But for me, this is too slow. So if I want to make this system faster, I have to retune my PI controller by changing the gain. The problem is that no pain, no gain. Making the system faster, you will have consequences, which is, for example, in this system, pushing your system more towards instability, more towards the limitations of the system. What are the limitations of the system? Out of physical constraints that we are dealing in every system, the most important one are the limitations in the actuators. For example, my valves. I cannot change the displacement in valve for infinity. I cannot give every voltage I want to pumps and motors. On the other hand, I have output constraints. I cannot put as much water as I want in the 3rd tank. It has a limited capacity. And at the end, if you have been ever working in chemical industries, you know that sometimes nobody cares that you bring your variables to a certain value, but most important thing is that to control them in the certain zone. So at the end, I would say that the zone control is one of the main important things that we skip PID controllers and try to go to MPC, which is taking more care of the constraints. For example, here, I'm making my PID faster, and then you see that I'm violating the highest admissible level of water in the 1st tank. I may reach the reference in a very good time, but I'm violating the limitations. So that is the main and important reason that one control engineer needs to design an MPC instead of one PID controller to take care of the limitations of the system. Thank you for your attention.
4 seconds. Perfect timing.